Okay, guys, let's get started. Today we'll continue to talk about commonly used method for NDT for concrete structures. Okay, we'll discuss impact method, ground penetrating radar, calorimeter, among others. So impact method is used by tapping on the surface of concrete using a hammer or dragging a steel chain on the surface of concrete and listening to the sound and to assess the condition of concrete. Okay. So a higher frequency pitch will indicate a good concrete. A lower frequency pitch indicate presence of flaws, such as hollow area underneath the concrete. But this concrete, this test method has its drawbacks. Okay. A trained operator can delineate the zones of high and low pitches using this method very quickly because just drag the steel chain over a large area of concrete is very easy, and also using a hammer to pound the surface of concrete is very fast. But the big advantage of this method is it depends on the skill level of operator, and also it does not provide quantitative information on the amount of damage inside of concrete. Okay. And because of these limitations, some other methods were developed, okay, such as impact echo. So this method can control the duration of impact force. As a result, we can assure the reproducibility of the test, okay, and can also somehow quantify the surface displacement generated by impact on concrete. Okay. For example, we can use the steel balls. Okay, use the steel balls to impact on the surface of the concrete. And then listen to the impact echo. Okay, so use of sensitive broadband transducer as the surface, and also analyze the waveforms in the frequency domain. Okay. Okay. As we can see here, it shows a couple of figures use impact echo method. Okay. So a well-controlled force by a steel balls, impact on the surface of concrete. So that's impact point. We also have a receiver on the surface. Okay. Based on that, we can use impact echo method to check, for example, the depth of the floor. Okay. Because depending on the depth of the floor, the frequency will change. Okay. For example, for the concrete structure like this, without voids, the frequency is lower compared to we have voids in the slab. Okay, so frequency will be higher because the distance between the impact wave and reflection wave is shorter. Okay, so based on that, we can detect internal floor and also check the depth of the floor. So here talk about a similar method. It's called spectral analysis of surface wave. Okay, so surface wave is also called Rayleigh wave. So R-A-Y-L-E-I-G-H. Okay, so remember last time when we talk about mechanical waves, we know we have a P wave, which is due to compression of the materials, and also we have R wave or shear wave, which is due to elastic response to shear. And also we have a surface wave or the Rayleigh wave. Okay. But actually, surface wave are not only confined to the surface. Okay, it can penetrate somehow to a certain depths depending on the frequency. Okay, so you can sense its property in a certain depths beneath the concrete. And waves with shorter wavelengths, the energy dissipation will be higher, faster. So you may not be able to sense this continuity deep in the concrete, okay, because the wavelength is too short, but it's very accurate. Okay. However, waves with longer wavelengths, it can penetrate deeper, but the resolution is not as high as short wavelengths. Okay. And we can change the velocity with different wavelengths to establish the layers of high and low velocities. Okay. So this is the spectral analysis based on Rayleigh wave or the surface wave. It's called SESW, spectral analysis of surface wave. The setup for SESW method, we have impact point. Okay. We also have analyzer. We could have multiple analyzer. Like in this case, we have a 2 receiver, 1 and 2. And this 2 receiver has a certain distance. And after the impact, okay, the impact will generate Rayleigh wave, a surface wave, which is received by the receiver 1 and 2. Okay. Because the receiver can easily measure the time difference when it receives the waves, and also the distance between these 2 receivers is fixed, very easy to measure. So we can translate that information into velocity and then into depth of layers. So that's impact method. The next method is called acoustic emission method, which is also based on mechanical wave. However, that's a big difference between these 2 types of method. So acoustic emission method is also a non-invasive, non-destructive method that will analyze the noises created when materials deform or fracture. Okay. So the energy, the wave, is generated by the material itself, typically when the material fracture. Okay. Not the same as impact method. For the impact method, we generate the force, the wave, using a hammer, a chain, or steel ball. Okay. But in this method, we does not apply the mechanical wave. The instrument only analyze and receive the wave. Okay. So acoustic emission wave propagates through the materials, okay, and then it can be detected on the surface by a sensor. Okay, the sensor will stay there for a long time because you do not know when the concrete will fracture. Okay, so we put a sensor there for days, weeks, or even months. Okay, when we have acoustic emission created by the fracture, then the sensor can detect it, okay, which will turn the vibration into electrical signals. Okay. And the sound of fracture, which is the mechanical vibration propagation, was called acoustic emission, okay, because it may be acoustic and audible. However, outside the audible range, which is between 20 to 20 kHz, we can still use this method. Okay, so not only limited to the acoustic range, audible range. Okay, so again, the crack is generated by the material itself, and then the energy, the signal is detected by the receiver, which is installed on the surface for a long time. Okay. the difference between acoustic emission method and the ultrasound method and impact method is in the ultrasound method, a known signal is imparted into the materials. Okay. So for example, a hammer, a chain, or a steel ball. Okay. And the materials response on signal is studied. But for the acoustic emission method, the signal is generated by the material itself. And we do not know when the signal will be generated because we do not know when the material will crack. Okay, but that's the major difference between these two methods. And here shows the typical result of acoustic emission. Okay, we can measure the amplitude, the duration, and the frequency of the signal. So the method we just discussed is based on mechanical wave. Okay. Then let's go to the other categories. These two methods we discussed before, polarization resistance and half-cell potential. Okay. So these are two methods to measure corrosion, which is covered in lecture 13, where we discuss corrosion of reinforcement. So one of the methods is to measure the probability of corrosion, okay? So which is the half-cell potential method. The other method, the linear polarization resistance method, measure the actual corrosion rate of steel reinforcement in concrete. Okay, because these two methods belong to non-destructive testing, so I just list here, but we do not repeat of these two methods. Okay, this is the half-cell potential method I used to use to measure the corrosion of this is called Tiger Creek. It's part of historical canal in Northern California. Okay. Next. Okay. Cover meter. Okay. This method has another name. It's called eddy current method. Okay. So let's look at the introduction for a cover meter. Okay. So cover meter can be used to detect metals. Okay. It is a generic term for equipment used to locate steel reinforcement in concrete or some other metals such as aluminum. Okay. As to estimate the thickness of a concrete cover, okay, we know there's a 1 or 2 inch of concrete cover above the steel reinforcement. It can also detect the size of the rebar and the space of the rebars for some time. Okay. So unlike concrete, steel bars interact strongly with low frequency EM waves, okay, which is applied at the surface of the concrete, so we can easily detect the location of the steel. Okay, the reason is because steel and concrete has very different electrical conductivity and also magnetic permeability. Okay, so eddy current method can detect materials with high difference in electrical conductivity and magnetic permeability. Okay. Here shows a typical setup for the instrument for cover meter. Okay. So that's the excitation coils, which are AC source. Okay. Okay. And also we have a ferromagnetic cores. The other side of the ferromagnetic cores, we have sensing coins together with the eddy current meter. Okay, so here the flux means the circulating magnetic current after we apply the exciting coins. Okay. If we have a steel or other type of metals near the magnetic field, okay, so the magnetic field will be changed and it will generate a secondary magnetic field, which will in turn change the reading for the sensing coil. Okay. So the eddy current is parallel to the surface of concrete. So the rebar need to be parallel to the setup of the calorimeter. Okay. So we can use calorimeter to do several things. For example, if there's a crack in a steel bar, sorry, not steel bar, steel beam or steel members. Okay, so we can sense the cracks, even tiny cracks in the steel members. We can even measure the thickness of paint on the surface of the steel members. Okay. For steel reinforced concrete, we can detect the location of reinforcement, depth of reinforcement, and even the diameter of the rebar. Okay. So basically, that's another name for calorimeter, which is the metal detector. Okay, it can detect metals. The next method, ground penetrating radar, is also based on electromagnetic wave, as in the case of calorimeter. Okay. So ground penetrating radar, they use high frequency EM waves. Okay. As we can see, the frequency is between 50 to 100 megahertz. Okay, so this is in the range of 1 gigahertz. Okay, it can send EM pulse with very short duration, around 1 to 3 nanoseconds, and analyze the echoes reflect back into the GPR machine. Okay. Again, depending on the frequency, the penetration depths may also be limited. For example, if the frequency is 1 gigahertz, the penetration is around 40 centimeter. Okay, so increase the frequency, we can increase the resolution, increase accuracy, but reduce the penetration. So GPR can be used in concrete to detect voids and delamination, but it is sensitive to voids and delamination filled with water. If the voids is filled with air, GPR is not very sensitive to that. Okay, so we're gonna talk about why that's the reason. GPR is very easy to locate the reinforcement. Okay, and it can also measure the pavement thickness and monitor the structure change. Okay. So GPR is affected by properties such as electrical conductivity and also dielectric constant. So basically, if two materials, such as steel and concrete, has high difference in electrical conductivity and dielectric constant, then it is easy for GPR to detect. Okay. But for air and concrete, for example, if the voids in concrete is filled with air, GPR cannot easily detect that because for air and concrete, the electrical conductivity is pretty similar. Okay. So GPR cannot see that. Some other application for GPR, we can use it to check the water content, or even degree of hydration, and also the presence of chloride. Okay. Again, it is sensitive to water content. Okay. So here shows how GPR work. So the instruments, including the transmitter, which is sort of TX here, and also the receiver. Okay. So sometimes the transmitter and the receiver is in the same unit, okay, and it can move along the surface of concrete with a wheel. The GPR does not necessarily to touch the concrete surface, which means you can remotely sense the concrete inside the concrete with a certain distance between the concrete surface and the instrument. Okay. So the machine will send EM waves. If inside the materials has two materials with two different dielectric constants, then the wave will be reflected back, okay, and detected by the receiver. Okay. And here shows how to use GPR to detect reinforcement. Okay. So TX is the transmitter, send the signal, and RX is the receiver, receive the signal. So because the dielectric constant between steel and concrete is high, so when the wave touches the steel, it will be reflected back and received by the receiver. So from there, we can detect the location, even size of the rebar. Okay. If we have multiple layers of rebar, okay, so not only one layer, but 2 or 3 layers, it may also be detected, but the second layer may be shadowed by the first layer. Okay, so here shows another setup for GPR. Again, the transmitter and receiver doesn't necessarily touch the surface of concrete. Okay, so no need to contact the concrete surface. Okay. If there's a voice, if the voice is filled with air, then GPR probably cannot see that clearly. If the voice is filled with water, because water and the concrete has very different dielectric constant, then the voice can be detected by GPR. For steel rebar, very easy to be detected. Okay. So again, it is difficult to detect air field defects, but it's very good for water field defect and steel reinforcement. Okay. And here shows the example of ICO. ICO is coming from delamination from bottom of the deck, okay, from the reinforcement, and also from the surface, because the antenna is not touching the concrete surface. Okay. So GPR can automatically give us the location, the layout of the rebar. Like this, here shows the example when I did for the Tiger Creek project. So the GPR can give us almost a 3D, we call that 2.5 dimensional map of reinforcement beneath the concrete. Okay, so we run the GPR in layers, different lines, horizontally and also vertically, all along the surface. And the instrument will generate a 2.5D maps or drawings for the rebar. Okay, like we can see from here, the red line are rebars. Okay, and this is the cross-section view. We have a different layers of rebar, and also we may have some delamination beneath the concrete. Okay. And also we can see the GPR has wheel, so we can easily run along the surface of the concrete. Okay. Any questions about the method we just discussed? All right. So again, these 2 lectures just briefly discussed a valuable method for NDT for concrete materials. Okay, so quickly go over the basics of this method. The next one is infrared thermography. Okay. Okay. So if inside concrete we have imperfections or voids with high porosity, okay, and then it may have different thermal properties compared to remaining part of the concrete. Okay, so these thermal properties including one, thermal conductivity, and two is the so-called heat capacity of the materials. Okay, so if inside the concrete we have two different zones, two different materials has different thermal conductivity and heat capacities, then we can use infrared thermography to detect that. Okay, so under heat flux, okay, we need heat flux to be able to use this method. They will produce zones with different temperatures, which can be detected by thermal cameras. Okay. Right. Such as here. So here shows effect of flaw or imperfection on temperature distribution of concrete slab. Okay. Right. So let's see, we have a air voids inside the concrete. Okay. Depending on how the direction of the heat flow. So if the heat is flowing from top to bottom, okay, and we have a camera on top of the concrete, then what we can see is the temperature in the areas above the air gap is higher. So we call that hot spot. Okay. So if the direction of heat flow is from bottom to top, and also we have camera on top of the concrete, and then we have a cold spot above the gap. Okay. So this method is only sensitive to cracks near the surface. If the cracks is very deep inside the member, the heat flow can go around the voids and affect the result. So only sensitive to surface crack. It is also sensitive to orientation of the crack. Okay, so imagine we have a crack not horizontally but vertically. Okay, and then the crack cannot effectively block the heat flow, so we may not see the hot spot or cold spot. Okay. So this method can be used to check if we have any delamination or if we have a debonding between reinforcement and concrete, and check the general quality of concrete. Okay. So I can show you the equation for this method. So this method is based on equation of thermal radiance, okay, which is this. Okay, so R is called thermal radiance. So in the units of watts per square meter. Okay, so E is called emissivity, emissivity of the materials. Okay. Emissivity for concrete, that value is about 0.95 or 1. Okay, sigma is constant, and T is the temperature in Kelvin. Okay. So as we can see, small change in temperature, we have big change in thermal irradiance, which in turn will be detected by the thermal camera. Okay, so that's how this method works. Okay. So this is another example of using thermal camera to see this is the corrosion of steel reinforcement in one of the reinforced concrete deck in San Francisco area. This is around 2007, 2008. Okay. So we use infrared thermography, also called night vision, to check the corroded areas, which doesn't have a lot of light. And this method can also be used to detect leakage on the roof. Okay. So if we have a leakage on the roof, and then if we have a heat flow, for example, from inside the house to outside the house, so during the night, we use thermal camera, and it can detect hot spot. Okay? Because if you have a leakage, that areas will have a higher temperature, can easily be detected by the thermal camera. And also around windows, you can see here. Okay, so heat is also going out of the house from the windows and certain areas of the roof. So we know how we can further insulate the house. Okay. All right. The next method, so tomography of reinforced concrete. Okay, it's getting fancier. So tomography, probably everybody has heard of this before. Tomo means slice in Greek words. Okay, so basically we use X-ray and some other radiation to give slice of the samples. Okay, and the goal is to imagine an object by taking measurement from many different slides and reconstruct the 3D image for the sample. Okay, and here's another name which is CT or computed tomography. Okay, we know we can use CT for in hospital. Okay, so we can use that for concrete also for research purpose. Okay. So for computed tomography, image of object will be reconstructed from projection of the object. Okay. We can take 2D slides or even 3D slices. Okay. So the image again will be reconstructed from slices of X-ray. X-ray is the most commonly used of radiation. Sometimes gamma ray can also be used. The X-ray and gamma ray, which is generated by radiation source, is rotating around the sample, around the object for a full 360 degree. Okay. And it will generate slice go through the materials. Okay. And then based on the attenuation of radiation penetrating through different part of the materials, okay, then we can generate a 3D image for that. Okay. So we can either do slice, which is parallel to each other, or we can do a 360 degree slice, like in this case. So we have a radiation source, okay, on one side of the specimen, and we have a detector on the other side of the specimen. Okay. And of course, we can only use this in the lab because the CT machine is very big, and also we have radiation. Okay, so we cannot use that in the field, only in the lab. And also we have limitation on the size of the specimen due to the limitation of the CT machine. Okay, but anyhow, let's look at some of the example. This is actually CT for concrete, so reinforced, fiber reinforced concrete cylinder. Okay, so the picture on the left is a typical radio graphic. That's a 2D image. Okay. The CT image is on the right, okay, which can give much more details. Okay. And again, this is the video graphic on the left and CT image on the right of a loaded fiber reinforced concrete. You can see the damage inside the concrete specimen from CT more clearly compared with the 2D radiographic image. All right, this is the microtomography. Okay, so the image, the scale is very small, only 200 micrometer for this lens. Okay, we can see the very detailed information inside the concrete sample. Okay. This is the 2D image, radiography here, and 3D tomography. All right, so this is for reinforced concrete column. So very clearly, you can see the advantage of 3D tomography. That's a 3D image. We can see the reinforcement cage inside that concrete column. Okay. Again, this method can only use in the lab for research purpose. Okay. And also that is very costly, but we can use that for concrete research. Okay, here is another type of tomography. It's called backscattering microwave. Okay, so microwave has very high frequency. As you can see, 300 million hertz to 300 gigahertz. So very, very high frequency. So that tells us two things. One is the wavelength is very short. In other words, the resolution is very high. Okay. The other thing is the penetration will not be deep. It will be very shallow due to dissipation of energy is very, very high. Okay. So it is microwave tomography. The big advantage is high resolution. So you can use that to detect details inside the concrete, but again, not very deep due to limitation on penetration depths. All right, so today's lecture and also last time, 19 and 20, we have a discussion on method, NDT method for concrete materials. Okay, we know we have many different type of NDT tests. Okay, and each one has its own benefit, can be used for certain specific jobs. Okay, there's no single NDT techniques is good for all jobs. So depending on the application, we should choose the right one. And also for all kind of NDT techniques, always use visual inspection first. Okay, and concrete inspection typically will perform as combination: visual inspection, non-destructive testing, and semi-destructive testing. Okay, together with traditional methods such as compressive strength, durability tests, and so on. Okay. So that's today's lecture. We are toward the end of semester. We have basically 2 more lectures to go. I think 2 or 3 more lectures. Next time we'll discuss microstructure analysis, including scanning electron microscope, X-ray diffraction method, mercury intrusion method. This is to analyze the porosity, the particle size distribution, and other microstructure property of samples, including cement and concrete. And then we have a final lecture, which is about retrofit, how to repair concrete cracks. Okay, and yeah, that's about it. All right, so that's today's lecture.